Hello, Ross. For lesson 6.1, our review of exponential functions. For the video, I want to review how we can use exponential functions to model growth and decay. There's a relatively simple format, or let's say formula, I suppose, that you can use for most exponential growth or decay functions. Actually, there's a couple of formats that you might want to be familiar with. So usually an equation in the format p of t equals a times b to the exponent t divided by h works fine. We have seen models where we need a shift before, where we don't have a horizontal asymptote of y equals 0. So all of these equations in this format have a horizontal asymptote of y equals 0. So if you have a population that shouldn't be decaying from 0 or away, growing away from 0, then maybe this model won't work. If you have a coffee cup that's cooling in a room where the temperature isn't 0, perhaps that equation wouldn't work. But it usually does a pretty good job for functions that we could imagine would have gone backwards towards 0 or forwards towards 0. In most cases, p of t is going to be your initial, p of 0 is going to be your initial population or mass or whatever. That's usually going to be A. Not always, but usually going to be A. P of t is your outputs, t is your input. Your base, B, is either your growth or decay factor. Like if we're talking about doubling or halving or tripling, I can use a number like 3 or 2 or 1/2. But our base could also be 1 plus r, or our b could be 1 minus r. This would be if we have a growth rate of r% or a decay rate of r%. I'm not quite sure I'm writing it properly. Maybe it should be 100% plus r. This is usually going to be as a decimal. Okay. In the same way with our exponent, we want to be sort of flexible here. If t is measured in some unit of time, then h can be measured in the same unit of time, and it can be the measure of your length of a period, a growth or a decay period. But really what we want is to make sure that our entire exponent counts the number of periods. It's sometimes easier just to make sure that your entire exponent counts the number of periods than it is to make sure that h represents the length of a period. Let's try it out by imagining a population p of t dependent on time t in years. So we're not allowed to be sneaky and change our independent variable here. And we want to write a function to model a population of 100. For part A, it says it grows by 5% every 2 years. So I'm going to have a final population, that is my initial population. To grow by 5%, I want my base to represent the 105% that I keep. So I'm going to use 1.05 as my base. Okay, my function isn't going to model just the 5% increase. It wants to model the increase on top of the original population. So this is 100% plus the 5% that I'm growing. Growing every 2 years, I could say, oh, in this case, h is 2 years, so I can do t divided by 2. I can also just then make sure that if p were equal to, if t were equal to, say, 6, that my exponent should be 3, because there are 3 groups of 2 years in 6 years. Okay. As a curve, if you want to visualize it this way, we begin, or we cross the y-axis, the dependent axis, at 100, and then we go up by 5%. We should be going through 105 after 2 years, 2, 105. So notice the vertical stretch to get us to an initial position of 100, a growth factor. We're increasing at a rate of 5%. And then the horizontal stretch by 2 makes it so that we don't grow by 5% until 2 years have passed. Okay. We can think of transformations, but we don't need to interpret this as a vertical stretch and a horizontal stretch. Very much like with trig functions. For question B. situation B, let's say we have a population of 100 and it is doubling. So I'm going to use a growth factor of 2. Doubling technically means that I'm increasing by 100%. Tripling means I'm increasing by 200%. It's a little surprising because our base is 1 plus our growth rate. Often when you say something's doubling, students think, oh, 200%. Or they might see it for doubling. For tripling, seeing that your growth rate is 200% it's a bit of a stretch. And this says it doubles 3 times in a year. So this is a situation where I think it's just going to be easier to have my exponent count the number of growth periods. If I, for example, wait for 1 year, my exponent should be 3. Well, what do I do to an exponent of t to change it to an exponent of 3 when t is equal to 1? I multiply it by 3. I think this is a lot easier than saying, oh, well, my function's going to be p of t equals 100 times 2 to the exponent t divided by, and 3 times a year means that my growth period is 1/3 of a year. So then I have t divided by 1/3. I mean, this is a mess because I shouldn't leave fractions over fractions. And then I see students that feel the need to continue to write divisions of fractions as a division of a fraction and then multiply by the reciprocal to get 3t like that. I think maybe easier isn't the best word. I think if you reason through it, this maybe demonstrates more efficiency than this approach. It might be harder to not just memorize a formula, but I think it's beneficial. Here on my curve, I have a vertical stretch by 100. I have a doubling curve. I stretch it vertically by 100 to get my dependent intercept where I want it to be. It's a doubling curve. And I want it to double 3 times in 1 year. So by the time I get to 1 year, it should be at, well, let's see, it would be 200, 400, 800, I guess, after 1 year. Or we're at 200 after 1/3 of a year. Notice the horizontal stretch by 1/3 brings me in, so that we double there. Make sure you don't try to convert your growth periods. Growing by 5% every 2 years is not the same thing as 2.5% every 1 year. Doubling 3 times in a year is not the same thing as being multiplied by a factor of 6 every year. Notice that we're not being multiplied by 6. Doubling every 3 years means doubling every 3 years. You can't convert those growth rates easily. It's quite tricky to do. It's a post-secondary skill. Let's try a population of 100 that is decreasing by 5%. So sometimes students, when they see decrease, they put in a negative. There is this idea of subtraction here, but take a look at what your sketch would look like. And recall that you don't deal with negative bases on exponential functions. You just want your function to lose 5% or keep 95% of its previous output. So that right there is your 100% minus 5%, the percentage that you keep. Every 3 years, well, let's do t divided by 3 and make sure that it takes 3 years to go by. So I should be passing through 3, 95, I guess. That's a horizontal stretch by 3. That'd do it. And the last one, population is halved. So half-lives are maybe a little bit trickier than sometimes students think. It's not the half that you lose, it's the half that you keep. And if it's halving twice in a year, well, then if I wait for 1 year, it should happen 2 times. Twice in a year. That means that this half-life is actually half of a year, but I don't think we should be writing t divided by 1/2 in there. It is an opportunity to use transformations of exponential functions to visualize how to get things to work the way that you want it to. Okay. Review any grade 11 applications on growth and decay if you're struggling with the prerequisite material there. And make sure that you really focus on those grade 9 exponential rules as well. That's probably the more important part of the lesson. Try them out.